Nuclear energy powers cities without greenhouse gases, but it leaves behind radioactive waste that's dangerous for thousands of years. Storing this waste safely is a huge challenge. If it leaks, it can poison our environment. Most solutions are expensive and complex, but a team of Egyptian scientists found hope in an unexpected place. Rice bran, a byproduct of milling rice. They discovered a way to turn this agricultural waste into a tool for cleaning up radioactive contamination. The idea? Use rice bran as a natural sponge to soak up radioactive ions from water, a process called biosorption. This breakthrough could make nuclear cleanup cheaper, greener, and accessible to countries everywhere. Rice bran is the thin brown layer removed from rice grains during milling, usually discarded or used as animal feed. For every ton of white rice, about 100 kilograms of bran are produced, creating mountains of this low-value byproduct worldwide. But rice bran is rich in natural chemical hooks that can grab onto heavy metals and pollutants. The Egyptian team saw its potential as a biosorbent, especially since rice is grown in massive quantities across Asia, Africa, and beyond. Instead of being waste, rice bran could become a powerful, renewable resource for environmental cleanup. It's sustainable, abundant, and available wherever rice is grown. Turning this overlooked byproduct into a pollution-fighting tool is a win for both agriculture and the environment. To transform rice bran into a radioactive magnet, scientists treated it with acid, cleaning and activating its surface. This process creates more active sites, tiny chemical hands ready to grab radioactive ions like cobalt and cesium. The treated bran, now a fine powder, is mixed into contaminated water, where it attracts and traps radioactive particles. Afterward, the bran is filtered out, leaving cleaner water behind. The radioactive-laden bran is much easier and safer to handle than large volumes of toxic liquid. This simple, low-cost method turns farm waste into a high-tech cleanup tool. It's a smart use of chemistry and sustainability. So does it work? In lab tests, the modified rice bran removed over 99% of cobalt-60, a dangerous radioactive isotope, from water. It also captured other harmful ions like cesium and strontium, key components of nuclear waste. The bran's high uptake capacity means a small amount can clean a large volume of water, making it practical for real-world use. Compared to expensive synthetic resins, rice bran is cheap, renewable, and widely available. This could slash the cost of nuclear cleanup, especially for countries with limited resources. The results are clear. Rice bran is a game-changer for radioactive waste management. It's proof that simple, natural materials can solve complex problems. This technology is a win for both the environment and the economy. By upcycling rice bran, we reduce agricultural waste and cut the need for costly petroleum-based cleanup materials. Rice-producing countries can use their own resources to tackle nuclear pollution, saving money and boosting local economies. This approach democratizes nuclear cleanup, making it accessible to nations everywhere, not just the wealthy. It's a powerful example of sustainable science, finding value in what others throw away. Nature's chemistry, harnessed by human ingenuity, could help solve some of our toughest challenges. The rice bran story shows that sometimes, the answer to a global problem is hiding in plain sight. With creativity and curiosity, we can build a cleaner future, one grain at a time. Welcome to For Science Salah Lotfy channel. In today's episode, we are proud to highlight the remarkable career and achievements of one of Egypt's leading experts in nuclear chemistry and radioactive waste management, Professor Dr. Emad El-Din Hassan Mohamed Borai. His name is well known across the Arab region and international nuclear science communities, not only for his academic leadership, but also for his pioneering work in the separation and purification of radionuclides and rare earth elements. Let us take a closer look at his inspiring journey. Professor Dr. Emad Borai began his academic path at the Faculty of Science, Ain Shams University, where he earned his bachelor's degree in chemistry in 1988. By 1993, he had completed his master's degree in analytical chemistry, and in 1998 he earned his PhD in analytical chemistry, all from the Egyptian Atomic Energy Authority. He was appointed assistant professor in 2003 and promoted to full professor in 2008. Dr. Borai's professional journey began in 1989 as a teaching assistant in nuclear fuel chemistry at the Hot Laboratories and Waste Management Center, part of the Egyptian Atomic Energy Authority. He later served as head of analytical chemistry and control in 2006. Today he leads the Hot Laboratories and Waste Management Center, one of Egypt's most critical nuclear facilities. His international experience is equally impressive. Between 2009 and 2011, Dr. Borai served as a visiting professor at the University of Helsinki, Finland, contributing to international scientific collaboration. Back in Egypt, he led major divisions in radioactive waste management and contributed to projects on separation and purification of naturally occurring radionuclides and rare earth elements from Egyptian minerals. In 2018, Dr. Borai's expertise was recognized regionally. He was appointed as a nuclear technology expert at the Arab Atomic Energy Agency in Tunis, supervising the nuclear technology department. This role highlights his capacity not only as a scientist but also as a policy advisor building institutional capacity across the Arab world. Professor Dr. Emad Borai's distinguished journey, from teaching assistant to international expert and head of Egypt's top nuclear waste facility, is a powerful example of dedication, innovation, and service to science and society. If you found this episode inspiring, please like, share, and subscribe to For Science Salah Lotfy channel. Leave us your comments below and join us as we continue highlighting brilliant minds shaping the future of Arab science. Welcome to the For Science Salah Lotfy channel. I'm Professor Dr. Salah Lotfy, and today I've got something truly exciting for you, a scientific breakthrough that's green, practical, and could change how we deal with radioactive waste. The study I'm sharing is titled Low-Cost and Eco-Friendly Biosorbent for Effective Removal of Hazardous Ions from Simulated Radioactive Liquid Waste. It's published in the Arabian Journal of Chemistry, Volume 16, 2023. This is a peer-reviewed journal from the Saudi Chemical Society, published by Elsevier and King Saud University. The paper was received March 30th, 2023, accepted September 6th, and published online September 11th. Now let's give credit where it's due. The lead author is Professor Dr. Syed Metwally from the Egyptian Atomic Energy Authority's Hot Laboratories and Waste Management Center in Cairo. He's joined by Professor Dr. Emad Borai, the center's head, along with Professor Dr. Mostafa Mohamed, Dr. Tarek Mohamed from the National Center for Radiation Research and Technology, Dr. Mahmoud Mohamed, and Dr. Walaa Mohamed, all from the same authority. That's a powerhouse team tackling a global challenge. So, what's the breakthrough? The team figured out how to take rice bran, yes, that leftover part from milling rice, usually thrown away, and turn it into a powerhouse for cleaning up radioactive waste. They modified the rice bran using acid treatment and gamma radiation, transforming it into what's called a biosorbent. This biosorbent can capture and remove hazardous ions like lead, strontium, and europium from simulated radioactive liquid waste. And get this, it does so with over 80% efficiency. The science? The process follows pseudo-second-order kinetics and fits the Langmuir isotherm model, which means it's a chemical adsorption happening in a single layer. Pretty neat, right? But here's what's even cooler. Rice bran is cheap, abundant, and local. In Egypt, and many rice-producing countries, rice bran is everywhere. Instead of spending big money importing high-tech materials or using energy-hungry processes, we can just use rice bran to clean up nuclear waste. That's a win for the environment, the economy, and public safety. Now think global. Places developing nuclear energy, especially across Asia, Africa, and Latin America, need affordable, effective solutions. This method is accessible and scalable. It's not just a lab idea, it could be rolled out wherever rice is grown and nuclear waste is a challenge. The team didn't just test this with one contaminant, they tried it with mixtures, just like in real-world nuclear waste. The rice bran biosorbent held its own, performing as well as or even better than many expensive synthetic materials. Sometimes, nature really does have the best answers. So, why does this matter? This research shows how we can use local, sustainable resources to solve national and international problems. It's science serving society, and it's a model for future eco-friendly technologies. Hats off to Professor Dr. Syed Metwally and the entire team behind this innovative research. Their work brings us one step closer to a cleaner and safer world. If you found this episode fascinating, please like, share, and subscribe to the For Science Salah Lotfy channel. Drop your questions or thoughts in the comments and stay tuned for more stories where science meets society. Thanks for watching. Consider the humble grain of rice. It feeds billions, yet we often overlook its outer layer, rice bran. For years, rice bran was just animal feed or waste. But science has revealed its hidden potential. Rice bran is more than fiber. It's packed with proteins, fats, vitamins, and minerals, all in a unique structure. Think of it as a natural sponge full of microscopic nooks that can grab onto things. This grabbing ability, adsorption, is its secret superpower. The surface of rice bran naturally attracts certain molecules, especially heavy metals. Researchers discovered its chemical makeup gives it a slight negative charge, perfect for attracting positively charged pollutants like radioactive metal ions. Rice is grown everywhere, so rice bran is cheap and abundant. Instead of being waste, it's a powerful, accessible solution hiding in plain sight. By using rice bran, we turn a low-value byproduct into a high-impact tool. Science helps us see the world not just for what it is, but for what it could be. Sometimes, the answers to big problems are right under our noses. So, how does rice bran clean up radioactive waste? Imagine contaminated water filled with radioactive metal ions. Add rice bran, and its massive surface area gets to work. Each piece acts like molecular Velcro, grabbing those dangerous ions. This process, called biosorption, uses rice bran's natural chemistry to lock pollutants onto its surface. Functional groups on the bran, like carboxyl and hydroxyl, are negatively charged, ready to bond with positive metal ions. In tests, rice bran removed over 95% of lead from water, and was highly effective with strontium and europium too. Once saturated, the bran clumps together, making it easy to remove from the water. The result: cleaner water, and a smaller solid waste that's easier to handle. It's a simple, natural way to tackle a complex problem. Sometimes the best solutions are the most straightforward. Why does this matter? Let's meet the villains: lead, strontium, and europium. Lead is a neurotoxin damaging brains and bodies even in tiny amounts. In radioactive waste, it's a major threat to health and the environment. Strontium-90, a byproduct of nuclear reactions, mimics calcium and gets stored in our bones where it can cause cancer from within. Europium, less famous but still hazardous, accumulates in bones and the liver, increasing cancer risk. These metals persist for centuries, contaminating water and soil. They're found in nuclear plant wastewater, medical facilities, and accident sites. Removing them is critical for public health and environmental safety. Rice bran's ability to capture these metals is a game changer. It offers a practical way to tackle a global pollution problem. Sometimes the simplest tools are the most powerful. That's why rice bran matters. Cleaning up hazardous waste usually means expensive, high-tech solutions. Traditional methods use lots of energy, harsh chemicals, and cost a fortune. Rice bran flips the script. It's green, clean, and affordable. It's a natural, renewable, and biodegradable resource, turning agricultural waste into a valuable tool. Using rice bran doesn't create extra toxic sludge or require massive energy. It's accessible. Rice is grown in over 100 countries and bran is cheap and plentiful. This means even communities with limited resources can use it to clean contaminated water. The process is safe and simple. Stir in the bran, filter it out, and you're done. No high pressures, no dangerous chemicals, just nature doing the work. It's a low-tech solution with high-impact results. Environmental cleanup doesn't have to be complicated. Sometimes the best answers are the most natural. As the world turns to nuclear power for clean energy, managing radioactive waste is a growing challenge. Rice bran offers a practical, scalable way to treat contaminated water, right now. It can be integrated into new nuclear programs or used to clean up legacy pollution. This discovery bridges advanced science and traditional agriculture, showing that big solutions can come from humble places. It's a reminder that innovation and sustainability go hand in hand. By respecting nature and using our ingenuity, we can solve even our toughest problems. Rice bran is more than a byproduct. It's a symbol of hope. With creativity and persistence, we can build a cleaner, safer future. Science gives us the tools. It's up to us to use them wisely. Sometimes the smallest things can make the biggest difference. Welcome back to For Science Salah Lotfy channel. Today I'm excited to walk you through the materials and methods that made our rice bran biosorbent research possible. So, how do you turn an everyday byproduct like rice bran into a powerful radioactive waste cleanser? Let's break it down step by step. First, I started with the basics. Chloride salts of europium, lead, and strontium, all sourced from Sigma Aldrich. Each of these was dissolved in pure bidistilled water to make standard solutions at a strong concentration of 1,000 milligrams per liter. For adjusting pH during the experiment, I relied on trusted acids, hydrochloric, nitric, phosphoric, and sulfuric acids, as well as a good ammonia solution. All of these came from reputable suppliers like Merck and Fluka. And of course, rice bran, the star of this project, was collected directly from local Egyptian rice mills, making it both sustainable and super affordable. Now let's talk about preparing the rice bran. First, I sieved, cleaned, and thoroughly dried it. Then I treated about 50 grams of rice bran with a 3% solution of phosphoric acid. I heated and stirred this mixture for 2 hours, then let it sit for a full day. The result? A fine, grayish-white powder. I experimented with other acids too, but phosphoric acid gave the most manageable and efficient material. The next step was irradiation. At the National Center for Radiation Research and Technology in Cairo, I exposed the acid-treated rice bran to gamma rays, between 10 and 30 kilogray doses. This step boosts the material's adsorption abilities. After irradiation, I washed the rice bran with acetone, dried it in an oven, and ground it into various particle sizes, ready for testing. But how do I know the rice bran is ready for the task? I use some high-tech tools. FTIR spectroscopy helped me identify the surface functional groups. SEM with energy dispersive X-ray mapping revealed the surface's look and chemistry. And X-ray diffraction showed the crystalline structure changes after treatment. One crucial detail, I determined the point of zero charge or pH-PCC by soaking the rice bran in potassium nitrate at different pH levels. This tells me at which pH the rice bran surface has no net charge, important for catching metal ions. Then, I tested biosorption efficiency across pH values from 1 to 6. After mixing and shaking overnight, I used flame atomic absorption spectroscopy to measure how much lead, strontium, or europium was removed. Finally, I challenged the rice bran with simulated radioactive waste containing a tough mix of ions, strontium, lead, europium, cesium, zinc, cobalt, and nickel. At pH 5, the modified rice bran successfully pulled out a whole cocktail of hazardous ions in just one go. So, with careful prep, smart chemistry, and detailed testing, rice bran goes from farm waste to a high-efficiency biosorbent, one that could help solve major problems in radioactive waste management. Next time I'll share the performance results and what this could mean for real-world cleanups. Thanks for tuning in. If you enjoyed this, hit like, share, and subscribe for more science stories. And tell me in the comments, do you think waste materials could help clean your country's future? See you next time on For Science Salah Lotfy channel. What happens to rice bran, the powdery leftover from milling rice? Usually it's waste. But now, scientists are using it to clean radioactive pollution from water. Radioactive materials like strontium are dangerous, so finding cheap, effective ways to remove them is crucial. Rice bran is natural, abundant, and inexpensive, perfect for biosorption, a process where it acts like a sponge for pollutants. Its surface molecules, like cellulose and lignin, grab onto harmful metal ions. This turns agricultural waste into a powerful environmental tool. Traditional cleanup methods are costly and can create more waste. Using rice bran is a win-win. It helps farmers and the environment. It's a simple idea with big impact, solving pollution with something we usually throw away. Nature gives us solutions in unexpected places. By rethinking waste, we find new ways to protect our planet. Rice bran, once overlooked, is now a hero in environmental cleanup. Sometimes the best answers are right under our noses. Let's see how science unlocks its full potential. To see how rice bran works, scientists used high-tech tools. FTIR spectroscopy revealed which chemical groups grabbed pollutants. X-ray diffraction showed rice bran's amorphous structure, full of nooks for metal ions. Scanning electron microscopes let scientists see the surface before and after biosorption. The difference was clear. Pollutants stuck to the rice bran. EDX analysis confirmed the presence of radioactive ions on the surface. Before, only plant elements. After, new peaks for strontium and lead. This was proof rice bran captured radioactive ions from water. These tools showed exactly how rice bran becomes a pollution magnet. Science turned a waste product into a powerful cleanup agent. Let's see how they made it even better. Scientists wanted to boost rice bran's power, so they zapped it with gamma rays. This broke down complex molecules, creating more sites for pollutants to stick. The result? Irradiated rice bran removed pollution even faster. Another key pH. The rice bran's surface charge changes with pH. At higher pH, it's negatively charged, perfect for attracting positive metal ions like strontium. By adjusting pH, scientists made rice bran a stronger magnet for pollutants. Particle size matters too. Smaller rice bran means more surface area, more spots for pollutants. Using tiny irradiated particles at the right pH supercharged the cleanup. Simple tweaks made a huge difference. This approach is efficient, low cost, and easy to scale. Science found a way to turn rice bran into a pollution-fighting powerhouse. But how does it actually grab onto the pollution? Let's break down the mechanism. Rice bran cleans water through ion exchange. A smart trade. Its surface swaps harmless ions like calcium for dangerous ones like strontium. Functional groups on rice bran have a strong attraction for heavy metals. The result, radioactive ions stick to the bran, while safe ions go into the water. Most pollutants are removed quickly, then the process slows as sites fill up. Scientists modeled this with the Langmuir isotherm, showing rice bran forms a single layer of captured ions. This helps calculate how much pollution rice bran can hold. The process is fast, efficient, and predictable. Ion exchange is the secret behind rice bran's cleanup superpower. So, what does this mean for our future? This research turns rice bran from waste into a powerful green cleanup tool. It's abundant, biodegradable, and cheap, ideal for treating radioactive water. The process is simple. Mix rice bran with contaminated water and let nature do the work. It's a circular economy in action. Waste becomes a resource. This method could help clean up nuclear wastewater and respond to emergencies. It's accessible even in remote areas. The success of rice bran opens doors for other natural biosorbents. Science shows us the hidden value in what we throw away. With innovation and respect for nature, we can build a cleaner, safer planet. Rice bran's story is a hopeful reminder. Solutions are all around us. Welcome back to For Science Salah Lotfy channel. Today I'm excited to bring you the final findings on how a simple biosorbent, modified rice bran, can make a real difference in environmental remediation. Let's kick things off with contact time and sorption kinetics. The research showed that rice bran absorbs radioactive ions like strontium, europium, and lead pretty quickly, hitting equilibrium at about 90 minutes. At first, the process is super fast because there's loads of space for ions to latch onto, but as those spots fill up, the rate slows down. Now, the team tested two kinetic models. The pseudo-first-order model didn't fit, but the pseudo-second-order model nailed it, with an R-squared value over 0.99. That means chemisorption, where electrons get exchanged, is the star player here. Moving on to equilibrium isotherms. How does rice bran perform under different concentrations and temperatures? Using the Langmuir isotherm model, they found sorption actually increases with temperature, so the process is endothermic. The max capacities? Strontium at 1.26 mmol per gram, europium at 0.76, and lead at 0.33. This fits the monolayer adsorption idea. The Freundlich model, on the other hand, just didn't line up with the data. But what about the real world? The team tested rice bran on a simulated radioactive waste solution packed with ions. Removal efficiency ranged from about 51 to 74%, with europium leading the pack. That proves rice bran works not just in perfect lab conditions, but in messy, real-life scenarios too. Now, how does rice bran stack up against other sorbents? Well, titanium phosphate, a synthetic, has higher capacity. But rice bran is cheap, eco-friendly, and easy to get, especially in places where you need large-scale cleanup. Let's talk about how it actually works. Rice bran is full of carboxyl and hydroxyl groups that swap out hydrogen ions for metal ions. For strontium and europium, that's 2 protons each. Lead mainly exchanges 1. The mechanism is backed up by FTIR spectra and a drop in pH after sorption. Clear evidence of ion exchange doing the heavy lifting. So, what's the bottom line? With pH at 5, a contact time of 90 minutes, fine particles, and a reasonable ion concentration, removal rates are impressively high, nearly 90% for strontium and over 80% for both europium and lead. The data fits the Langmuir model and follows pseudo-second-order kinetics, pointing strongly to chemisorption. Before I sign off, huge credit to the research team led by Professor Dr. Syed S. Metwally, with valued contributions from Dr. Emad H. Borai and colleagues. This work was supported by the Science, Technology, and Innovation Funding Authority. Here at For Science Salah Lotfy channel, we celebrate scientific teams turning waste into opportunity. If you learned something today, hit like, share, and subscribe. Let's keep turning knowledge into real-world solutions. Before we end this episode, as Professor Dr. Salah Lotfy, professor at the Egyptian Atomic Energy Authority, and on behalf of For Science Salah Lotfy channel, I would like to extend my sincere thanks and deep appreciation to the distinguished research team behind this remarkable study. Special thanks to Professor Dr. Emad Borai, the head of the Hot Laboratories and Waste Management Center, Egyptian Atomic Energy Authority, for his excellent supervision and scientific visualization. Professor Dr. Syed Metwally for his leadership in conceptualizing, administering, and drafting this vital research. Dr. Mostafa Mohamed for his precise validation work. Dr. Tarek Mohamed, for providing essential research resources, Dr. Mohamed, for his valuable efforts in data curation and formal analysis, Dr. Walaa Mohamed, for her contribution in software support and investigation. Thank you all for your outstanding scientific contribution. Your work is a true example of how multidisciplinary research can serve both science and society. To our esteemed viewers, thank you for joining us. Please share your thoughts and reflections on this research in the comments section below. Your feedback inspires dialogue and helps bring science closer to the public. Until next time, stay curious and keep supporting science. This is for Science Salah Lotfy channel, where science meets community.